purpose of my talk tonight is to introduce you to a famous and important mathematics problem called Fermat's last theorem. It's important because the study of it has led to many new developments in lots of different areas of mathematics, and it's been tackled by the greatest mathematicians of the century, since the problem is over 350 years old. It's only a year ago that a proof was finally announced, and then a gap was perhaps found in the proof, and there's been quite a bit of maybe confusion in the media about exactly what the status of it is right now. So I'll be introducing you to the statement of the problem, to its history, how it came about, and why it's as famous as it is, some of the results that have, in progress that's been made, and then we'll go to the recent proof announced by Andrew Wiles from Princeton, and see what about his proof also. So to help motivate the presentation tonight, I want to show you a clip from the Wizard of Oz here, in which right after the witch has been Dorothy threw water on her and she melted. We'll pick it up right after that. I know that's your favorite part. You probably want to see it, but we don't have time to watch all of it. So you probably recall that when Scarecrow receives his diploma from the wizard, he makes a mathematical statement. And I want you to pay attention to that statement and see what you think about it.
Why have you come back?
Please, sir, we've done what you told us. We brought you the broomstick of the Wicked Witch of the West. We melted her.
Oh, you liquidated her, eh? Very resourceful.
Yes, sir. So we'd like you to keep your promise to us, if you please, sir.
Not so fast. Not so fast. I'll have to give the matter a little thought. Go away and come back tomorrow.
Tomorrow? Oh, but I want to go home now.
You've had plenty of time already.
Yeah. Do not arouse the wrath of the great and powerful Oz. I said come back tomorrow.
If you were really great and powerful, you'd keep your promises.
Do you presume to criticize the great Oz? You ungrateful creatures think yourselves lucky that I'm giving you audience tomorrow instead of 20 years from now. Oh. The great Oz has spoken. Oh. Pay no attention to that man behind the curtain. The great Oz has spoken.
Who are you?
Oh, I am the great and powerful Wizard of Oz.
You are? I don't believe you.
No, I'm afraid it's true. There's no other wizard except me.
You humbug!
Yes, it's exactly so. I'm a humbug.
Oh, you're a very bad man.
Oh, no, my dear. I'm a very good man. I'm just a very bad wizard.
What about the heart that you promised Tin Man? And the courage that you promised Cowardly Lion?
Well, I'm Scarecrow. Why, anybody can have a brain. That's a very mediocre commodity. Every pusillanimous creature that crawls on the earth or slinks through slimy seas has a brain. Back where I come from, we have universities, seats of great learning, where men go to become great thinkers. And when they come out, they think deep thoughts, and with no more brains than you have. But they have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum e Pluribus Unum, I hereby confer upon you the honorary degree of Ph.D.
PhD?
That's Doctor of Thinkology.
The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, Joe, Rapture! I've got a brain!
You hear what the Scarecrow said? We won't. I know you probably want to talk about the part about coming out of a university with no more brain than you have, but the Scarecrow's statement was the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Is that right? Okay, the sum of the square roots, let me go back there to, I went past it. the sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Now, first of all, you recall what an isosceles triangle is. That's where two sides have the same length. The third side need not necessarily have the same length. So according to the Scarecrow, if you take the square root of any two sides and add those up, take their sum, then it will equal the square root of the remaining side. Now, I've drawn a triangle here on the next page. And it's an isosceles triangle because two sides I have labeled with the same length, x, and the base is perhaps a different length, so I labeled that y. Now, he said any two sides, right? So let's start maybe with these two sides. The square root of those two sides, square root of x and the square root of y, when I add them together, take the sum, should add up to the square root of the remaining side. Is that right? So if I take the square root of x plus the square root of y, it should add up to the square root of this side? No, I don't think so. You've already got the square root of that side right here, right? So certainly if you add the square root of y, you would come up with a quantity greater than the square root of x. So we already have good reason to question Scarecrow's brain, I think. Yeah, even after his PhD. Well, let's see if we can salvage something. Maybe he didn't mean to say any two sides. Maybe he meant to say those other two, the two co-equal sides. Perhaps that's the case. So let me look at the other two sides. Perhaps the sum of the square roots of those two sides would add up to the square root of the bottom side. You think that might be possible? Now, the way I've drawn it, it looks like they're so long that when you add them up, they surely would be greater than the square root of the bottom side. But then you can't really trust a diagram, because I could have drawn the base to be much, much longer, right? So let's write down what they have, the sum of the square roots of those two sides. Now, let's see what kind of progress we can make here. You have square root of x plus square root of x. That gives you twice square root of x. You have two of them. Okay. Now I'm going to do a little, well, let's say a little clever thing here that you'll agree is legal, but why I do it, you may not see why. I claim that 2 square root of x is greater than square root of 2 times square root of x. Now, I think you'll readily agree with that, because 2 is bigger than square root of 2. I left the square root of x alone. So you'll agree that's a legal thing to do. But why did I do that? Okay, well, I'm going to put these two under the same radical sign here and make that square root of 2x. Now, we were talking about this triangle in which you have the two sides like this and then the base like this. Suppose you wanted to travel from the left-hand side of the base, let's say right there, over to here. What's the shortest distance between those 2 points? To go on the straight line on the base, correct? You wouldn't want to go up here and then way down here. On any triangle, 2 sides will add up to more than the third side. That's the triangle inequality. Well, these 2 sides right here add up to 2x, and 2x is what I got right here. I needed 2x, not 2 square root of x. That's why I put in the 2 being bigger than the square root of 2 here. Because now I can say that 2x underneath the radical here, 2x is greater than y, so square root of 2x is greater than square root of y. So now we have the following line here. The sum of these 2 sides is greater than, in a couple of places, the remaining side. So therefore we weren't able to salvage in the Scarecrow's statement in the way I proposed it. In fact, no 2 sides will add up to, the square roots will add up right. All right, well, I'm not ready to give up on his brain yet. What might he have meant to say? Let's, this is what he said. The sum of the square roots of any 2 sides of an isosceles triangle is equal to the square root of the remaining side, which we now know is a false statement. Have you ever heard a similar type mathematical statement, though, perhaps? Maybe this one. The sum of the squares, not the square roots, the sum of the squares of the two legs of a right triangle, not an isosceles triangle, is equal to the square on the remaining side. Now that's the Pythagorean theorem. Now that's well known. We know that's true. Maybe he meant to say, or maybe the writers meant to write, that the Pythagorean theorem instead there. Let me give you some examples of those kind of triangles. I've shown some here. See, a right triangle, that's an angle of 90 degrees here. And I've labeled it x, y, and z. So we have the squares adding up rather than the square roots. Here's a couple of famous ones down here. The 3, 4, 5 triangle, because 9 plus 16 is 25. And here's another one, 25 and 144 is 169. So there's a couple of well-known right triangles. Maybe that's what he was getting at. All right, now, we know square roots don't work. We know squares will work. Let's carry it a little further. How about cubes? Could I make third powers work, or fourth powers, or fifth powers? Let's do some experimentation. Can you think of some numbers which, when cubed, will add up to another cube? Well, if I just said numbers, so you certainly could do it with, if you just use numbers, like for example, I could take any old numbers, 1 and 2, they add up to 9, and you could cube the cube root of 9, and that certainly would work, but that's not very satisfying. See, the 3, 4, 5 triangle is so nice, 5, 12, 13, but to have cube roots, irrational numbers, you know, the Greeks didn't even recognize the existence of the irrational numbers such as that. What if we just stick to integers? I guess I'll have to stick it to positive integers, because if you allow negative numbers, then you could easily do it too. So the trivial cases like that I don't want to consider. Let's just stick to using the positive integers. Well, now I don't think of one right off the hand. You could try some examples. Maybe what's 1 cubed plus 2 cubed? That's 9. 9 is not the cube of a positive integer. Okay, 8 would be, but not 9. Well, I don't know, make up some other ones. 2 cubed and 3 cubed, what's that? That's 8 and 27. 8 and 27 is 35. Now 35 is not the cube of a positive integer, right? Well, you might experiment for quite a while, and you may either think that you just haven't stumbled upon it, but it's out there somewhere, or that maybe it's not possible for the sum of 2 cubes to add up to the cube of another integer. So that's getting us towards what the statement of Fermat's last theorem is. Fermat was reading a book by the ancient Greek Diophantus, and in which Diophantus had given a number which is a square, write it as the sum of 2 other squares. So 25 can be written as 9 plus 16. 144, we saw, can be written as 25 and... No, 169 could be written as 25 and 144. So Fermat generalized the statement and wondered if perhaps third powers or fourth powers could be similarly written. And he came to this conclusion, which he scribbled here in the margins. He said, on the other hand, it's impossible, Fermat claimed, for a cube to be written as a sum of 2 cubes. And he said a fourth power to be written, or in general, for any power greater than the second, to be written as a sum of 2 like powers. So this is Fermat's last theorem here. He claims that no, you'll never find cubes that add up to a cube. Not only that, but you won't find fourth powers that add up to a fourth power of a positive integer, nor fifth powers, nor sixth powers, nor any power at all. And he further scribbled in the margin that this statement down here. I have a truly marvelous demonstration of this proposition, which unfortunately the margin of the page was too narrow to contain. Now, he wasn't necessarily just blowing off steam when he said that. Fermat was the top mathematician of the 1600s. Okay, he was just about the top one. He was of an entire century to be the number one mathematician. And he made important contributions to lots and lots of areas of mathematics. So if he says he has a proof, he may well have one. But the trouble is, you see, it's called Fermat's last theorem because we never discovered this marvelous proof that he had. Perhaps he had it, perhaps he didn't. He didn't publish any of his mathematics. His son, after Fermat died, took it in hand to publish quite a few things just by going through his old papers. And Fermat did correspond with a lot of people and informed them of his results and showed the proofs of several things. But no one's ever come across this marvelous proof that he claims to have. And for 300 years since then, 1637, for 350 years, the best mathematicians of the centuries have been trying to prove this and have failed. Gauss, Isaac Newton, Euler, the great mathematicians of the 20th century, none of them have been able to prove this until perhaps just here recently in 1993. Now, did Fermat really have a proof, or was he perhaps mistaken? Well, the general feeling is surely he was mistaken. Maybe he thought he had a proof, but it had a mistake in it. It's not. Fermat made other mistakes. He claimed that if you take 2 to a certain power and add 1, that would be a prime number, and that turned out to not be true later on. Of course, he didn't claim he had a proof of that, though. He just conjectured that. He said, I think this is the case. Now, lots of people make conjectures. Every mathematician has made conjectures that are wrong, so you can't really hold that against him. But there has never been a case where Fermat said he had a proof of something and that turned out to be false later on. That's never happened. And like I said, he was a top-flight mathematician. If he said he had a proof, in fact, if he said he had a marvelous proof, look, it is, the word marvelous, though, that tells you something. If one of the most brilliant people is impressed enough to say, boy, this is marvelous, then you got to think, well, boy, there's a chance he came up with something that nobody else for 350 years has come up with. That's conceivable. They don't really think that's the case, but they certainly can't rule that out. Now, so here's a picture of Fermat and the statement of his last theorem. And here it is written in modern notation down here. If n is greater than 2, then this equation has no solutions in the positive integers. Now, we know if n is equal to 2, we've seen some solutions, but if n is greater than 2, Fermat claims that there will be no solutions in the positive integers. Now, let me look at some partial results that have come through the centuries. They've worked on this problem. They didn't lick it, and perhaps until recently, but there were some partial results. Fermat himself, although he didn't provide the marvelous proof, he did write down this proof. He proved that the fourth powers will never add up to a fourth power. He did provide us with that proof, but he didn't prove any other powers. Although you can make this statement: if the fourth powers won't add up, then neither will the eighth powers. Now, why is that? Because the eighth powers are fourth powers, because they're a multiple of 4. Here in more detail, suppose the eighth powers would add up. Well, then you could write them as fourth powers because the square, the fourth power would add up. But we know fourth powers won't add up, so this can't happen. So therefore, we know that the eighth powers can add up once you know the fourth powers can't. And of course, likewise, the 12th powers won't, the 16th powers won't. Any multiple of 4 won't work, and he established that in writing. Okay. And you also see now we've taken care of really an infinite number of exponents, all the multiples of 4. If we could take care of 3, you'd get all the multiples of 3, 5, 7. Now, you wouldn't have to do 6 because 6 is a multiple of 3. You would only have to do the prime numbers, numbers which are not multiples of other numbers. Yeah, you'll need to establish it for third powers, fifth power, 7th, 11, 13, 17, the prime numbers. Now that 4 has been taken care of, and other than 2, which is a prime number, but we know it works for 2. So the mathematicians set about working on the remaining prime numbers. So we had in 1770 Euler, top flight, really the best one of the 1700s. He managed to prove it for third powers. Look here, that's 140 years later, 133 years later. So it took an awful long time to come up with that, just to go from the fourth power to the third power. So now that you got the third power, you got the 6th, 9th, and all other multiples of 3 taken care of. Then Legendre here, another 50 years later they worked on it, and he took care of the fifth power. And in the 1840s, a few people got together and took care of the seventh power. Now, they started looking at these proofs for the fourth, third, fifth, and seventh. Noticed some common ideas, common elements that were happening in these, and a mathematician named Kummer made a big advance then in 1850. First came, though, a false proof, which almost had it, by Lamé. He gave a presentation in which he claimed he had proven the entire theorem, and almost immediately, I don't know if it was right at the same lecture or right after, but almost immediately Liouville found a flaw in his proof. It was based on the same kind of reasoning that Euler and Legendre and Fermat had used. What they had done was they had factored the left-hand side, you know, the x to the n plus y, like the x cubed plus y cubed. You can factor that into x plus y times another polynomial. And if you continue factoring, you'll have to use complex numbers, which involve the square root of -1. If you continue factoring, you can factor it down into to its prime parts. Just like, for example, with the number 6, we can factor the number 6 into 2 times 3, right? And we can factor the number 12 into 2 times 2 times 3. We can factor it down into its prime factors. So what Lamé did is, borrowing on his intuition about the integers, he presumed that complex numbers could be factored uniquely the same way that integers can. 6 can only be factored one way in integers, as 2 times 3. But with complex numbers, and certain combinations of complex numbers, it's not the case that they can only be factored one way. In fact, the number 6, if you allow complex numbers, we can factor it a different way, like this. See, here's an imaginary number, the square root of -5. If you multiply 1 times 1 and square root of -5 times square root of -5, you get 1 minus -5, which is 6. Okay, and now you would have to show that these can't be factored to show that they're prime in the complex numbers. But Lamé had overlooked that fact that the integers can only be factored one way, but complex numbers, that's not the case. That turned out not to be crucial in the proofs of the third and fifth and seventh powers, but when you try to prove it in general, that turned out to be some cases where that didn't apply. So what the Kummer did here was he proved that if n is a regular prime, and that's really the cases that avoid that problem. He proved that if n is what he called a regular prime, then he could prove it. But the irregular primes, he couldn't prove it. Now the regular primes, they're pretty sure, they don't know, but they conjecture that they make up about 60% of all the prime numbers. So that's a pretty broad swath he cut through the prime numbers there. He took care of more than half of them right there, although it's never been proven. It's never been proven that that 60% is he proved it for regular primes, but we don't know how many regular primes there are really, although they've gone way up into the great big numbers, and they haven't found an end to them, but they're pretty sure, but not positive, that 60% roughly. They do know there are an infinite number of irregular primes, but that's kind of unfortunate. That's on the wrong side. But there's only 3 irregular primes less than 100. I think 59 and I can't remember the other 2. But Kummer also proved them for those 3, but he had to do it on a case-by-case basis. 59 he had to treat special and just use some special features about 59, was able to prove it, and then the other 2 with some other little different tricks, and then he didn't go any further. It was a piecemeal process with the irregular ones, and so it was a great progress, but the irregular primes are still left over. Now what Kummer did to overcome some of the problems with the factorization problem is, all right, integers won't factor uniquely, complex numbers won't factor uniquely over complex numbers, even though integers do. But he created a new theory called the theory of ideals, in which what's called a principal ideal, he proved, can be factored uniquely as a product of prime ideals. And the ideal is just a set which has certain properties, and it kind of generalizes the concept of the factorization of prime numbers. And ideals, this is where ideals first came from. Ideals get used all the time. Even a statistician like me, I had to study ideals a little bit, but even though that's in abstract algebra and numbers, that's not my field, but that's an important concept, the concept of ideals. So we see here one of the cases where the study of this perhaps seems otherwise unimportant problem, Fermat's last theorem, has led to new mathematics that have proven important in other fields. Oh, did you know there was a mathematician whose life was saved by Fermat's last theorem? That was Wolfskehl. Wolfskehl in the latter 1800s was depressed and really despondent and was going to commit suicide, really. And then he came across Kummer's work on Fermat's last theorem and his impressive contribution, and he became so engrossed in going over the Kummer's work that he came out of his depression, and he worked on Fermat's last theorem for the rest of his life. Didn't make any major contributions to it, but he became so enamored of it that in his will he established a prize that when he died, he'd give 100,000 marks, Deutschmarks, out of his estate to anybody who would solve Fermat's last theorem in the next 100 years. He died in 1907, okay, September 13th, 1907. So if anybody dies, pardon me, if anybody solves the problem before the year 2007, has to be before September 13th, 2007, they'll get this Wolfskehl prize. It's down to 10,000 marks now, though, because it got wiped out by inflation, you know, in Germany. So it actually got completely wiped out, and then they had to take up a collection. Mathematicians contributed because they thought it was a shame that they ought to get something out of it. But so now, see, we're at 1995 right now, and the prize has not been awarded yet, but you still got 12 years to go. All right, now I said that Kummer handled all the regular primes and 3 of the irregular primes. Well, in the century since then, in the 140-some years since then, through 1993, various people, lots of them, have picked away at these irregular primes, one at a time, and using the computers especially here, since the computers came around, they've managed to handle all the irregular primes that are less than 4 million, okay? So not only are all the numbers less than 4 million, but all their multiples above 4 million are all taken care of. So if there are integers who add up, their powers would have to be greater than 4 million. You might think that would be sufficient, okay? Scientists would accept that as conclusive evidence. But let me show you a similar result, which you will see in mathematics. We can't be like that. I have a question for you here. Do you think that 991 n squared plus 1 is ever a perfect square if you let n be a positive integer, like 1 or 2 or 3 on up? We can try some experiments. Let's start with 1 and just work our way up for a while. Here, I'll make a little table. Let's suppose we use n equal 1. Put a 1 right here. Now you take 991 times 1 squared plus 1, give you 992, right? Now that's not a perfect square. That's 31.4 when you take the square root. 31.4 something, something, something. So that, it's not a perfect square in that case. Well, let's try 2. No, you you get 62.9. 3, no, that's not a perfect square. Et cetera, et cetera, et cetera. No. You might try for as long as you please. You might experiment on the computer. Oh, the computer can do billions of operations per second. You might just set it to work and have it go for a couple of weeks or until you get tired. But you would find that it is possible to get a perfect square, and the first such case is when n is this number. 12 octillion, 55 septillion, 735 sextillion, 790 quintillion, 331 quadrillion, 359 trillion, 447 billion, 442 million, 538,767. That's the first time it happens, and it happens infinitely often after that. Okay? So now there's more evidence that the sun will come up tomorrow than there is pardon me, I should say there's more evidence that this will never be a perfect square than there is that the sun will come up tomorrow. Okay, I said it backwards. Yet we just can't accept in mathematics evidence. Okay, you got to have proof. So this is an illustration of that. Well, Wiles, in his proof, has gone off in a completely new direction. Rather than piecemeal picking away at these irregular primes and hoping that maybe you'll run into a counterexample, or else that some flash of insight will handle these irregular primes, a group of in number theory has gone off in a completely different direction, and it's unexpected. It's not how you would this was the brute force method that Kummer and such were using. They just tackled it from first principles, and lots of times that works, but sometimes more creativity is required. Wiles and his cohorts here have used the theory of elliptic curves. Now I'll have to explain what an elliptic curve is. An example of an elliptic curve would be the graph of this equation. This is one example of what's called an elliptic curve. Now, when you graph an equation, of course, you use numbers here for x and y, and you plot them like this. Okay? This turns out to be the graph of that equation right there. We've plotted various points. Let me show you here some of the points I plotted. Look here at this one, 8, 0. Okay, you see if you put an 8 right here that you get 0 on the right-hand side? Yeah. Or how about 0, 0? There's the origin. If you put a 0 here. Or how about a negative 27 right there? Negative 27, 0. Some other ones appear. Negative 12, 60. You'd have to multiply it out maybe with a calculator, but you get 3,600 over here. So negative 12, 60, and negative 12, negative 60 work. Number theorists have been studying elliptic curves because they have a lot of interesting properties, it's been discovered. One of those is that if you draw a straight line through two rational points, okay, a rational number is the ratio of two integers. If you draw a straight line through any two rational points on an elliptic curve, it will intersect the curve again in another point, and that point will be rational also. So number theorists are especially interested in rational points, and they're not that interested in the irrational numbers. So that's not that hard to prove. You could prove it here. You get the equation of this line, and the y you could substitute in here, and you get a cubic equation. You know two of the roots already. The third one would also have to be an integer because from the quadratic formula, that square root, knowing that two of them is an integer, the third one will also have to be. So what the number theorists have been doing here is they've been studying the rational points on these elliptic curves, and now this is interesting. They've been doing it in only finite number systems. They, an example of a finite number system would be on the clock. I don't see a clock in here, but there's only 12 numbers on the clock, right? That's a finite number system. What time is it 1 hour after 12 o'clock? It's not 13 o'clock. It's 1 o'clock, right? They only have a finite number. Now, that's modular arithmetic. So the The number theorists do a lot of work with modular arithmetic and finite number systems. And part of the reason for this is in a finite number system, only being a finite amount of numbers, some properties maybe are easier to prove than if you have an infinite number of points that you have to plot. So they plot maybe just a finite number of points, but they use bigger and bigger finite sets. So maybe we'll use 100 points, 100 numbers, then 1,000, 10,000. We'll see what properties hold in each of those. And as we get larger and larger finite sets, perhaps some of those properties will carry over in the limit to an infinite set of numbers. Perhaps they won't. You'd have to show that. But some properties perhaps carry over to an infinite set. So they've been working on these kind of things, and that leads to this name modular here. An elliptic curve is called modular if you can find some formula for the number of rational points in each of these finite number systems. So it's a little more technical actually, but that's essentially what that means. Now it has been conjectured, not proven yet, but conjectured that every elliptic curve is modular. Now they can examine elliptic curves on a case-by-case basis and prove that they're modular, and so far every one they've examined has been turned out to be modular. But of course we won't accept that as proof that all of them are modular. But it has been conjectured, Taniyama and Shimura conjectured that every single elliptic curve is modular, and Wiles has been working on this. Now the real breakthrough, though, if you ask me, came here in 1985. This mathematician Fry conjectured, didn't prove, but conjectured that if you can find integers a to the n plus b to the n that do add up to c to the n, then this elliptic curve here, which uses that same numbers, a to the n and b to the n, then this elliptic curve will not be modular. Now, I don't know how, that's an immense amount of creativity here to come up with a conjecture like that. See, he pulled in, it didn't seem like it had anything to do with Fermat's last theorem, some of the initial things we had, although I guess maybe to the people who are really experts in it, maybe it did. But this is the kind of creative leap, even though it's not a proof, that really leads to the breakthroughs. It's one thing to use existing methods to solve a mathematics problem. It's another thing to create your own methods to solve a mathematics problem. That's quite a different subject. So this was a real breakthrough when this conjecture was made. The one I graphed had an 8 here and a 27 here, didn't it? It had 2 cubed and 3 cubed. But of course there is no, that adds up to 35. That's not the cube of another integer. So now in 1986, Ribbett from Berkeley proved that Fry's conjecture was indeed a true statement. So what that amounts to then is if there's a counterexample to Fermat's last theorem, then there'll be an elliptic curve which is not modular. So therefore, if you can prove that all elliptic curves are modular, then there can't be a counterexample to Fermat's last theorem, so Fermat's last theorem would be proven then. And as a matter of fact, it turns out that not every elliptic curve would you have to prove it, only the ones that are of that particular form. Not every elliptic curve is of that form. So that's what Wiles did here in 1993. It looked like he had a proof that this particular curve is modular. So according to Ribbett's result up here, then that would prove Fermat's last theorem. So he presented this in 1993 at Cambridge. That's where he got his PhD in '77. And but see, I have a question mark here because about 2-3 weeks later, the other experts were looking at his proof and they found a gap, and it was a disabling gap. Although it perhaps it could be taken care of. He acknowledged his gap in an email message in 1993. You can get the latest on the email of what's going on with this. And somebody else called into question his proof, Have you ever read Parade magazine? And do you ever see this column by called Ask Marilyn by Marilyn Vos Savant? She got the highest IQ in the world, okay? Highest IQ in the world, so she claims. And she... yeah, right. She has lots of math problems, real interesting ones in there. And she's usually right on the money on her comments on them. One of the famous ones was, you ever watch Let's Make a Deal? And you have Monty Hall, and at the big deal at the end with the 3 doors. Now, the way that game always works, you guess which door the grand prize is behind. It's behind one of them, but you don't know which one, you just guess. And then Monty Hall always shows you one other door first that has a goat behind it or some booby prize. And then he asks you if maybe you want to switch. Would you rather take door number 2 instead of the one you have? You've seen there's a goat behind this one here. So do you think it would be to your advantage to switch to the other door or not? Some people would say yes, some would say no. Some would say, well, he can always show you a door with a goat behind it because he knows where they're at, and so therefore that hasn't changed anything, so it's irrelevant whether you switch or not. Some people would say that. Others would say, well, it's true that it doesn't change your chances of being right. That's true. You still have a 1 chance in 3 of being right, but that means you have 2 chances in 3 of being wrong, so there should be 2 chances in 3 that other door that remains is the right door. So you can kind of, if you think too hard about it, it seems like you can confuse yourself into to believe in anything. But she gave a very good example, which clarified it, I think. She said, well, suppose you have 100 doors, and only 1 door contains the right prize. And suppose after you pick, Monty Hall then reveals the contents of 98 other doors, all of which are goats, leaving only, like you chose door number 27, and he reveals all the 98, except number 87, for some reason, he leaves that one alone. Now, would you hop over to that one and take that one? You would. Now, she was correct. Your best strategy in that situation is to switch every single time. Now, you'll have a 2/3 chance then of being correct, and you still got a 1/3 chance of being wrong, but that's better than the 2/3 is better than the 1/3 chance, right? So ordinarily she is correct on these. Now here's what she wrote in her column of November '93. Has Fermat's last theorem been proved or has it not? I would say it has not. If we reject a hyperbolic method of squaring the circle, we should also reject a hyperbolic proof of Fermat's last theorem. Now, what's this hyperbolic business? Squaring the circle, that's a famous ancient Greek problem. To construct, using only a compass and a straight edge, a square which has the same area as a given circle, to square the circle. And it has been proven that in Euclidean geometry, that's impossible. It can't be done. But in hyperbolic geometry, it can be done. But we live in a Euclidean world. Well, maybe I shouldn't say that. If you're going to draw on paper, on flat paper with a straight edge and a compass, that's Euclidean geometry. That's not hyperbolic geometry. And it certainly is true that you wouldn't say, well, it can be done in hyperbolic geometry, so therefore it can be done in Euclidean geometry. No, you never say that. It's also true that in Weyl's proof, he does call upon hyperbolic geometry, but he doesn't say essentially, well, we can prove Fermat's last theorem in hyperbolic geometry, so therefore it must be true everywhere. He never makes any claim like that. Every statement he makes that refers to hyperbolic geometry could be translated out of hyperbolic geometry and not involve a hyperbolic argument at all. So there's really nothing to what she's said in this case, but I don't take away that she provides a lot of good arguments on some cases. But this is definitely not valid what she's saying here. In fact, here's what some of the experts say about Weyl's proof. He said, Weyl's work is not a mere chain of reasoning, which is only as strong as its weakest link, which really a proof is, a chain of reasoning. I mean, one gap in there, and you don't have a proof. So it's true that he acknowledged a gap, and he didn't have a proof. But they say that this is a bedrock of ideas, solid and rigid, a rich and profound new theory that will hold up even if a few details need altering. Now, what they mean is, okay, it hadn't been proven yet, But he created vast new ideas and areas of mathematical interest, which are going to lead into lots of new directions in number theory, for sure. He proved part of the Taniyama-Weil conjecture. That's not argued. In fact, it appears that maybe the entire proof of that conjecture would be at hand, which would unite really two separate fields of number theory, the elliptic curves and the modularity arguments. Here's Ribbett. He's another about the other top expert in the area. He said of Weil's talk that it was a complete revelation, which is really still shaking number theory. So they have concluded that it is significant. And here, just about 6 months ago, Weil's released a patch in the proof. It's only 17 pages long compared to his original paper, which is 200 pages long. So I guess it's too large to contain in the margins of my paper here. But in the 6 months since then, he circulated this, of course, to all the experts, and they've not been able to find a mistake in it. So it appears at this point, like I said, they were finding mistakes 3 weeks, 1 day after some of these other guys did it. Now they've been looking at it for 6 months now, and it's just a 17-page paper. Of course, you know how terse these things are, so it's not firmly established yet. They haven't awarded the Wolf Scale Prize, but it appears that he has in fact cracked it here and proven Fermat's last theorem. This is Andrew Wiles at Princeton. There's where he's at. When you think about it, how the great mathematicians over the last 350 years have been working on this problem, and to have all of those guys fail, and for us to be around when the proof has taken place, that it makes it a significant time in mathematics, and there'll be lots of ramifications of this in mathematics you can safely say, for centuries. If you need more details, they're going to have a little presentation at Allegheny College here in a couple of months, where they'll go over the details of this. This will be for people like me. It's not really my field, but I could get something out of it. So each day they're going to take a few more topics: modular forms, it's advertised, elliptic curves, the easy part, then the fancy part, then fancy part of modular forms, and then finally on Friday they get down to Weil's theorem. See, they call it a theorem now, as well as Ribbett's proof. And gee, they're going to tackle Weil's 200-page proof on the last day, on Friday, along with Ribbett. And his was another 200-page proof. All these proofs a lot of them are gigantic proofs. They build upon other people's works. It maybe makes you wonder that these proofs are so massive and rely on so many other massive proofs that even Weil's he's referring to some things that he's taken for granted. There's papers that's been published, and he's accepting these results because they've been published and been around for a while, but he's not actually going through all the details of those papers. He's taken them as accepted facts. So when they build proof upon proof, massive proofs like this, it does lead at least some question in some people's minds as to whether that's a valid proof or not. Now, there have been cases where theorems have been accepted for a while and then later discovered to be false. They've been maybe for 40 years. They'll be in the literature, and then somebody will find some mistake in it, and it turns out it's not even true. They'll find a counterexample. That's not happened with really big theorems, important big theorems, but it seems conceivable that could happen to sometimes. Well, if you want to get some more information on this, I have my presentation. You can see it's on HyperStudio here. It's on my Macintosh. If you're on the Mac Lab, if you're on the Macintosh network, you can access my machine by logging on as a guest and just pull this presentation off onto your machine. if you want to look at it. You have to know how to use HyperStudio, of course, but you feel free to look at it whenever you wish. All right. Well, I thank you for your attention. I'll try if you have any.
When did you,
Yes? Yes, go ahead, Laurie.
when did you first discover that the phrase that the scarecrow gave
Was relevant to...
was false?
was false. Well, I actually didn't think about it until a couple of years ago. Actually, it was because of my kids, okay? So I've got a 8-year-old, a 6-year-old, and a 3-year-old. So recently we've been, in the last few years, watching a lot of kids' movies, okay? Like The Wizard of Oz. And we got it on tape. Now, once you watch it 20, 30, 50... You start to try to amuse yourself with thinking about, I want to be in the same room with them, so I don't want to leave the room. So I start thinking about some things like this. There's other movies where they play pretty loose with the mathematics. It's probably in your fields too. Just about every field they play pretty loose with some of these things. But you like to think about it. So a couple of years ago I was thinking about that statement, and it doesn't take much to see that that's just a blatantly false statement. Yeah, John?
Do you ever think that maybe Fermat might have sort of been kind of near the end of his life or something when he wrote that in the margin and just thought, well, this will keep him going for a while?
Well, that's conceivable. I couldn't eliminate that.
I mean, when he writes down he's got this really marvelous proof. I don't know a whole lot of mathematics, but I think of marvelous proofs as something that you can say in about 2 sentences. 3 equations, and oh my gosh. And this 200-page tome doesn't seem quite as marvelous.
No, I'd agree with that. Nobody's claiming that this is the proof that Fermat had, okay? That doesn't seem possible. But it does still seem remotely possible that he did have some really marvelous proof. They don't think so. In fact, they think that maybe he made the same mistake that Lamé made there in 1847 about the factorization business, because that's the kind of idea he used to prove the x to the 4th plus y to the 4th one. And they think maybe he was just a little too quick and said, oh, you can do the same thing for any integer. But they don't have any evidence of that. They just think perhaps that's the case. Yeah, Lynn? Yes. That's right. He was using the existing methods of the time, just like a scientist of his day would use the existing instrumentation and such. Yeah, so... No, I don't know about that. That essentially was the brute force method is what they did, and they picked away at these exponents, but there's an infinite number of them. You can't very well have a computer establish an infinite number of statements as being true.
He probably didn't, but we'll really never know if he didn't have some just, nobody else ever thought of it, and it's really typical. There was a mathematician at the University of Chicago several years ago who was routinely assigned as homework to actually answer one of the most famous problems that had never been solved. He routinely assigned it along with the homework and didn't tell us who it was assigned. And one student, the day after it was assigned, came in and had it solved. Nobody thought it was supposed to be hard.
Yeah, that's right. That's right, yeah. Yes?
Mike, you talked about the ramifications, if in fact this is true. So say something about what they would be. We know there'd be more mathematicians running around.
Well, that's right. They'd be, like I say, it's opened up. He created brand new mathematical methods, Wiles did, in his proof. And new mathematical objects, new mathematical features which can be applied to many other areas of mathematics now. And he's really expanded the frontier of mathematics and made it wide open there, at least in the area of number theory and perhaps other areas. So that, yeah, there'll be lots of work now for mathematicians, lots of grants maybe. But,
Can I use the words that I used to talk about that? What you said in terms of opening up. If you would effective words to point in those directions.
for example, the...
What opens up these new frontiers? It's going like this, a whole lot of things.
Mhm.
They sort of talk to each other. What kind of words are these?
Well, the elliptic curves and modularity, that's the two big areas. See, those were sort of separate areas of number theory before, but Wiles' proof has united those. And that's brought together, kind of like a unified field theory, you know. That's brought together some disparate areas of mathematics now, which is going to allow a simplified, although it sounds complicated, simplified approach to some new things, and a lot of other progress now is certain to be made. Yes?
A couple of questions. The first one is more serious. I taught geometry in high school a few years ago and can remember the torture of trying to do a couple of 15 or 20 line proofs, getting from beginning to end without getting totally muddled. How on earth does somebody do 200 pages of that and still have track of where they are?
He started right away. He'd been working on it. He'd been an expert all along in elliptic curves. That's why he got his PhD in '77. So he'd been working on it all along. That's his research. In '86, as soon as Rivet proved the conjecture that's how you could crack Fermat's last theorem, he worked straight through. He worked, this is interesting, he worked, I wouldn't say in secret, but it was not a collaborative effort. You hear a lot about collaborative efforts. You see a lot of papers published. Gee, you look at the New England Journal of Medicine, they got 20 authors. It takes up about the whole page. But he did this absolutely by himself, using only one other colleague as kind of a sounding board, you know, just so he didn't get off the deep end. And so he immersed himself in this work as already one of the leading experts and worked on it for 6-7 years here straight. You know, Princeton, they don't have to teach that many courses. That's all he did day after day for 6 years, was work on this.
My second question was, is his proof sufficiently complex and incomprehensible that they might be able to balance the federal budget?
Well, I don't know. It could be.
Any other questions? Well, Michael, thank you again. We've enjoyed it immensely tonight. We appreciate all your good work.
I was glad to do it.